Section 4.2, we're going to take a look today at prime and composite numbers. And the very first thing we're going to do is to define what each one of those means. Prime, any positive integer with exactly two distinct divisors are considered prime numbers. So, after you write down the prime definition, just pause for a second and look at me. By this definition, which is the definition for prime numbers, is the number 1 prime? No. The number 1 is not prime. I know, he doesn't get to join the party. No party for number 1. So what's the first prime number then? 2. Okay, so let's list a few of the first ones just to remind ourselves. They're not a closed list, right? But I can list a few of them. 2 is the first one. What's next? 3. 4 is not. Why is 4 not? Yeah, because it's also divisible by 2. By itself, by 1, and by 2. What's next? 5 works. 7. Can I just skip all the evens? I can skip all the evens, right? Like 2, 4, 6, 8. After I do 2, I can skip all the rest of the evens because they're divisible by 2. So I don't even have to consider the evens. 7 works, but I don't get to include all the odds, which I think is what you thought I was asking. Yeah, I don't get to include all the odds because like 9's the next one, and that doesn't work. But I only have to consider the odd ones. So 11, yes. 13, yes. And then I skip 15 and go to 17. And we could continue this list for quite some time before we even run into numbers that we couldn't figure out quickly. Okay, so this list continues, but this is a few of them. Composite then. Composite numbers are any positive integers with more than 2 distinct divisors. Now, I'm not going to make a list on these of an extensive list, but we've come across a couple right now already. We came across the number 4 and the number 9 and the number 15, right? And of course, there's plenty more that I didn't even just write down between those here. There's lots of them, but those 3 would work. Yes, ma'am?
Is there like a set number of prime numbers?
Nope.
So like a finite or it's infinite?
No, there is no proof for a largest prime as of yet. And something would indicate somehow in my mind that thinks that there's probably not a largest prime. So since there's not a largest number of prime number, there's not a fixed number of prime numbers. Yeah. But there's no proof for that either, just so you know, that says that it's an indeterminate value. They just don't have. I got other more important things to do than find that, so I think we'll just let that one lie.
Are there equations to figure out whether it's a large number is prime?
I think you're going to encounter one in your book that's an example of it generates some prime numbers, but there isn't anything that generates like a formula for all of the prime numbers. The best that we're going to be able to do as we decide if something's prime or composite is to decide if in fact it does have any other factors besides itself in 1, and that's what's going to determine it for us. Okay? Factorization is exactly that. It's an expression of the number in its factored form. Gretchen?
Can we figure out if something is prime or composite by going through basically what we did in 4.1, like running through all of the...
That's a good place for us to start, and we will in fact do it that way. We won't include all the divisibility rules that we used in section 1. We'll only include the ones that include primes. That's the easiest way to do that when we do prime factorization. So I'm going to show you, I don't know if we'll get through all of them today, but several ways of determining factorizations and writing those down. So prime factorization is one of them. That's the last one on this slide. And it's a factorization that breaks it down finally and completely into its sort of lowest common terms, which is the prime factors that it divides by. And so our goal as we do factorization in the end is always going to be break it into its smallest pieces. Okay, that's what prime factorization is. So the first one we're going to do is the number 23,660. You know automatically that this is not prime. Why? Yeah, it's divisible by 2. It's an even, right? We know it's not prime. There are 2 basic ways to do the factorization on this. One is a factor tree. Do you guys remember factor trees? Okay. So we break this down, and you can divide it by anything it divides by. So honestly, when I see the 0 in the end, I think 10. So I do 10 and 2366. And you don't stop any branch until it's primes at the end of the branch. So like 10 is not stopped because it can be divided further. So 10 is what? 2 and 5. Now 2366, I'm sorry, what was that?
I said we got it.
Yes, here on that piece we did, but we're not done, right?
Right.
Over here on the 2366, I mean, I don't look at that like I did the first one and say 10, I know something. I just look at it, and the best I can do when I look at it is say, I know it's even. How about you guys? Okay, so when I put the number 2 here, that's kind of the best I can do just because I don't know of anything for sure that will go in other than that. So it's okay if that's all you know. And then if I divide this, I get 1183. Yeah. 2's prime, so we need to be careful not to lose track of him. So I'm kind of circling the prime numbers that sort of stop the end of my branches as I go, just so I don't, when I go back and look for them, I can find them all. Now 1183, again, I know it's not divisible by 2 now, right?
Yep.
Is it divisible by 3? No, how do you know?
So that's
Yeah, the sum. It's the sum, right? The sum of all those numbers, 11, the 1, 1, 8, and 3 is what? 13, and 13 doesn't divide by 3, so 3 is no good. Is it divisible by 5? No. And we don't have a test for 7, so we're just going to have to use our calculator or a longhand and figure it out. So Elisa has a calculator, so does Megan. Do either one of you try 7? Did it work? Okay, good. So 7 worked. What did you get when you divided it by 7? 169. Now 7 is prime, that's why we chose to divide by it, so we're going to circle it. 169, you may recognize that one as what? It's 13 times 13. If you didn't recognize it as 13, you'd pick back up where you left off. You were doing 7s. Try dividing by 7, see if it works. If it doesn't, you go to the next one, 11. Try dividing by 11. If it doesn't work, you go to the next one, 13. You will get there, okay? So even if you don't recognize it right off the bat, you can still continue through the prime numbers to check them. So these are the ends of my branches. So my prime factorization will look like the multiplication of these things. The order isn't truly important. However, just for sake of simplicity, we usually go smallest to largest. So the smallest prime number is 2. And how many 2's are there? There are 2 of them, so we're going to write this as 2 squared. And as we write them down, I'm going to cross them off. Okay? What's the next smallest digit that's dividing factor? 5, right? And there's only one of them, so I don't have to do anything different there. And then 7, right? And there is one of them. And then I have the 13. And there are 2 of them. So it's 13 squared. Notice between the 2, the 5, the 7, the 13, I've put the standard dot. If you want to put the X for multiplication, it's okay. We're not doing any algebra in this class, so that would be all right. By the time kids are doing this, mostly they've been introduced to the dot, so I think that's probably a standard form that they're going to see it in at this point. If not, you could also use parentheses around each of those as a third kind of option. So either the dots, the X for multiplication, or parentheses. They need something between them. Okay, so you can't just put them next to each other. That's not acceptable. And you definitely can't put a symbol like addition or subtraction because that's not the correct symbol, okay? Now, there's another way to do this method besides factor tree. A factor tree is much like in writing, to me, like bubble clusters. Did you guys ever do those with writing where you did these sort of like brainstorming sessions where you did, they called them bubble clusters when I was in high school. And so you kind of just wrote down these ideas that you had and you tried to sort of make them into your essay when you were done, okay? That's kind of how I feel about factor trees. They work, they allow me to go in any order, and that's handy, but one of the things that happens if you're not careful is you can lose a factor along the way because the ends of the branches don't all end up at the same point when you're done. So you do need to be careful to be a little bit organized with them. So this other method is a division method where you have a little bit more structure. So this is sort of what I liken to an outline. I think in terms of outlines. I think in terms of an organized structure of things. So this one appeals to me for that reason. Okay? There is structure to this one. You always divide by the lowest prime number that works. You don't get to divide by anything you want. So you have a little bit more structure imposed upon you as well. So the first lowest number that divides this prime is the number 2. So I will divide by 2, and you're welcome to have your calculator out to do these divisions. I don't expect you to do these longhand. What would this give you if you divide 23,660 by 2? Fabulous. And you ask yourself the question again, does this divide by 2 again? And of course, the answer is yes, so we'll do it again. So dividing this by 2, we get what? Okay, looks good. Does this divide by 2 again? No. So I do not need to try 2 ever again because I have finished all the 2's. So we go on to 3. Does this divide by 3? I don't think it does. Did you add them up? What does it add up to? 20? And 20 won't divide by 3. So this one don't divide by 3. So then we go on to 5's. Does it divide by 5? Yes, because it ends in a 5. So if you divide this by 5, what do you get? 1183. Do you recognize that now? We've seen that once before on the other method for doing this. Okay, I do not need to look again at 3's or 5's. I'm done. I mean, 3's or 2's, I'm done. Does it divide by 5 again? No. So then we go to the next one, next in our list of primes, which would be 7. And we would find out that it does, in fact, divide by 7, and we get 169. And then you probably, at this point, again, might recognize this one. If you don't, you could try 7. You can try 11. Eventually, you'll land on 13 working. And you have a 13 here and here. So it's sort of like an upside-down division, right? You're writing them on the side and down instead of going, going up on top. And the cool thing, and again, I like because the answers are all right here. So they are all in the same place instead of being spread out on the paper. They're a lot harder to lose in this method. The answer, of course, is the same. 2 squared times 5 times 7 times 13 squared. Okay, same answer. So your book will never tell you how that you have to do this. So if you absolutely love tree diagram or the factor trees, sorry, then you can do that. That's fine. If you like this method, you can do that. That's fine. There's not even a name for the second method, so it's not like I can say use this arbitrary thing that I did in class that don't have a name for. So I don't have a way really to describe this for you in an effective way. So just 2 different ways of thinking about it. Okay? All right. The next problems look a little bit different than the first one. The first one was just a solid number. You go from that. Yes, Ms. Gretchen.
I have a question on the
Oh, I'm sorry. Yes.
number. Would it not be confusing if you finish it in that way to a child? You have 13 in the end. Would it be okay if I write another box, put 13 beside it, and then end it in a 0?
Well, but it doesn't end in a 0.
Because it would technically
You would end in a 1. And so the goal when you're writing all these is that the end of the tree branch or the end of this diagram is done when you end up in a prime number. So the reason this stopped when I got to the 13 down here in the bottom is because 13 is prime, which tells me I'm done.
Okay. And so then that bottom number is supposed to be one of the branches.
It is one of the factors. Yeah, every number that comes out in the division is in fact one of your prime factors. Mm-hmm. Yeah. Okay, this one over here does not have a composite full number when you're started. It's sort of like partially factored, right? Okay, so it would be very counterproductive to multiply this all back out. Are you with me? It's already partially factored. Don't make more work for yourself by multiplying it back out. So what should I do instead? Well, I think the best option is to consider each of those pieces that are not quite prime numbers and factor them individually. So like if you did 16, you can do 4 and 4, 8 and 2. 4 and 4 is kind of nice, so I'll do a factor tree to show this. The 4s are then 2's, right? So this piece of it so far is actually 2 to the 4th, where the 16 was. But the 16 is currently already raised to the power 4 as well. So this 2 to the 4th replaced the 16, and the 4th that was already on the 16 is still there. Okay. We're going to do the same thing with 81. Can you factor 81 for me? 9 and 9, and each of the 9s factors into 3's. So this is 3 and 3. So then 81 becomes 3 to the 4th, and that also has a power of 4 in the original problem right here. Right? Okay, next one, 6. 6 is what? 3 and 2, or 2 and 3. So now we have, replacing the 6, 2 times 3, which looks a little different than the last ones I did, to the power 6. Okay, everybody good so far? Yes. This is in prime factors, agreed? I have only prime factors now, so almost all the way there. I just need to clean up the fact that I've got powers raised to powers, and that just looks a little awkward, and I've got 2 in there twice, and I've got 3 in there twice. I need to consolidate what's there, okay? So using the powers and properties of exponents that we did back in chapter 3, what do you get when you have 2 to the power of 4 raised to the power of 4 again? Right, good, it's 2 to the 16. You multiply the exponents. What are you going to get for the 3 raised to the power of 4 twice? That would be 3 to the 16. And then, what do you do when you have 2 times 3, quantity of that, raised to the power 6? 2 to the 6th and 3 to the 6th. Everybody good so far? So we're sort of just using those properties of exponents to clean up all the parentheses, really. And then repeated values can be combined. I've got 2 to the 6th and 2 to the 16th, which is 2 to the what? 22nd, very good. And I've got 3 to the 16th and 3 to the 6th, which is 3 to the 22nd. Okay? Everybody good with that?
Wait, how do we get 2 and 3? Sorry.
How do we get the 2 and 3 here?
No, the answer, like the answer. So.
Well, we compiled all of this. Are you good to this step, Lauren? Okay. So we took the pieces that were alike. This is 2 to the 16th, and this is 2 to the 6th. So we've sort of just rearranged the bases. Yeah, so those both of them have base of 2, so we can combine the exponents with addition.
Okay.
Okay. Any other questions?
Would
Yes.
it be 2 to the 22nd times 3 to the 22nd, or not times?
No, the base exponent rule says that if I have 2 to the 16th times 2 to the 6th, this is basically having 16 2's and then 6 2's, which means you have a total of 22 2's. That's 2 to the 22nd.
Okay, but in the
Oh, I know what you mean. Right here?
Yeah.
Yes. Thank you. I did leave that out accidentally.
I didn't know if it was written different.
Yeah, I left them out along the way even. When you have the exponents, it's almost understood. The problem is that you don't always have the exponents, so if you didn't, like if you had a single value to no power, or it looked like it didn't have an exponent power, then things look funny without the dots. Yeah. Okay. Another one. How is this one different than the last one? Yeah, it's not all multiplication. There is addition involved as well, right? Okay. So this one feels a little different than the last one because of the addition. But are there some pieces in common between the 2 sets of addition?
The bases?
Yeah, they have the same bases, 3, 2, and 7. Some of them have the exact same base and exponent even, don't they? Yeah. So that's the ones that we're going to look for first. So what we're looking for is we're looking for pieces that are common to both terms. So the first term has a 2 squared, and the second term has a 2 to the 4th. So what do they have actually in common? 2 squared. The first one has 2 2's in it, the second one has 4 2's in it, so they have 2 2's in common. So the first thing I'm going to do is I'm going to write down the part they have in common, which is 2 squared. So right now I'm just going to write down on the list, and then I'll tell you what we're going to do with it. How about the 3's? How many 3's are in common with each of the terms? 4. One of them has 4, one of them has 5, so they have 4 in common. How many 7's do they have in common? Yeah, all of them actually, right? 55 of them. Okay, so far so good? Cool. What we're doing with these is we're going to factor them out. So, the first value, there was a 2 squared, and I took out 2 squared of them, so this piece went away. I pulled it out in front. The second one was 3 to the 5th, and I pulled out 3 to the 4th. So how many 3's are left? 1. So I'm going to write 3. If you feel the need, you can write to the 1 power to remind yourself that there's a 3 to the 1 left. How many 7's are left? None. I took them all out, right? All 55 of them have been pulled out, so there's nothing of that left. Now, there's still an addition sign here. That doesn't go away anywhere. And we're going to do the same with the second set. 2 to the 4th. How many of them did I take out? 2 of them. So how many are left? 2 of them. So there's a 2 squared left here because I removed only 2 of the 4 2's. How about the 3's? This is 3 to the 4th. How many 3s are left? None. I already removed all the 3s, right? How about the 7s? I already removed all of them. Okay. Now, there's nothing to be done with the part on the outside. It is 2 squared times 3 to the 4th times 7 to the 55. I mean, none of that changes. But what's inside that set of parentheses can be simplified. It is 3 to the 1 plus 2 squared, which looks an awful lot like the number 7. Can I combine that with the 7 in front of it? Sure, no problem. So how many 7s are there? 56 7s.
So what do you do with the exponent from the 2?
I multiplied, yeah. So I actually did 3 plus 4 here to give me the 7, right?
Yep.
Fancy, huh? Yeah. All right, let me see if we have time for one more. You know what? We'll stop there because the next part actually all kind of goes together. It's a good stopping spot.